Welcome everybody to today's a session of Discrete Optimization Talks, or DOTS. We are happy to have Álinson Xavier today. He's going to be our only speaker for the day. So we have a little bit more relaxed schedule. Feel free to ask Álinson questions in the chat throughout the talk, and we will also have time for questions with Álinson afterwards, as well as a little bit more time for socializing for anybody who wants to stick around until, let's say, like half an hour after the talk, so that we can hang out with and catch up. Álinson Santos Xavier is a computational scientist at Argonne National Lab in the Energy Systems and Infrastructure Analysis Division. His research focuses on solving challenging computational problems that arise daily in the production and transmission of electrical power through a combination of mathematical optimization, high-performance computing, and machine learning. Dr. Xavier holds a PhD in mathematics, combinatorics and optimization from Waterloo, and he holds a master's in computer science from Universidade Federal do Ceará, Brazil, or Ceará. I don't know how the CEARA pronunciation is. Álinson will correct me about that later. And he'll be presenting today about MIPLearn. So with that, Álinson, please take it away.
Yeah, thanks a lot for the introduction, Alex. Also, thanks for the invitation here. So today I would like to talk about MIPLearn, which is this open source framework for learning enhanced optimization that we have been developing at Argonne. And this is joint collaboration with Georgia Tech, so Shantanu and two of his students. So before I present the MIPLearn framework itself, I'd like to start with a brief motivation on why did we even start this line of research, which is related to power systems optimization. So if you're not familiar with it, it turns out that optimization is used quite often in power systems domain. And in fact, the utilities and grid coordinators rely on a number of optimization problems daily to operate the grid. So I just listed a few of them here, such as optimal power flow, economic dispatch, UC, transmission expansion planning, and there are a lot of others. So what we have been seeing recently is that these problems that they rely upon pretty much daily to operate the grid are becoming increasingly challenging to solve. There are a number of reasons for that. The first reason, for example, is that the problems are just becoming larger. You now have larger networks, a lot more devices connected. You also have more participants in the electricity market, such as financial institutions. A second reason is that we also now have more complex units than historically we had before, such as battery storage, which integrates the time periods together. We have also some complicated types of power plants, such as combined cycle power plants. And the third and also most important factor is renewables. So what renewables brought to the table is that now you need essentially a finer time granularity. So before it was fine modeling things at, for example, hourly scale, but now because renewables are so volatile and they change the output so frequently, you really would like to reduce that to maybe 15-minute or 5-minute intervals, and that really blows up the size of the problems. So of course, all these problems have been studied a lot in the literature. So there's a lot of formulations and things like that. But what we have seen recently is that the progress in computational performance has been very incremental and has not really caught up with all this increasing complexity. So we are looking for other opportunities, like other alternative directions to really try to accelerate the solution of these problems. And one thing that we noticed was that in traditional algorithms, we always assume that these problems are being solved just once in a one-shot approach, and then the solver has no further access to what it did in the past, or it really cannot assume anything about the instance. But in practice, the way these problems are solved in power systems optimization is that they are solved repeatedly with some relatively minor variations. For example, the loads change every day, the costs change every day, maybe a few units go offline, maybe small changes in the transmission, but mostly the problems are the same day to day. So the idea here is, can we learn how to solve these problems instead of solving them in a one-shot approach? So this idea of learning to optimize is, of course, not new. I listed a few papers here from the 90s, actually, where they tried to solve a few of these problems, in particular unit commitment, using neural networks. And they did get some success to a limited extent. But all these approaches that try to replace Meep solvers by machine learning, they run into, I would say, two main issues. The first one is how to guarantee that the solutions provided by ML are actually feasible and optimal. So this was a big challenge that it's still being studied today. How do you enforce that? And the second one is that it was also hard for them to scale this up because these problems are pretty large scale. So another research direction which has been growing popularity recently is instead of entirely replacing Meep solvers by machine learning, can we use machine learning to essentially enhance their performance, right? And the nice thing here is that you benefit from both all the previous work that people have done in Meep research and Meep formulations, but you also benefit from any advances in machine learning. So people have been studying, for example, can we learn how to branch? Can we learn how to run heuristics? Can we learn how to run decompositions, how to select cuts, and so on? I have a brief illustration here on the side that kind of compares the two approaches. So in the traditional one-shot approach, you have your data, you provide it to the solver computes a solution, and then you use a discarded. And then the next day, all the solver has to work with is essentially the data for the new problem. It doesn't know anything about the previous solutions. And what we are proposing instead is that after you provide the solution, you essentially give that to some sort of learning module. And then in the next day, when you have a new problem to solve, the solver not only has the input data to work with, but also has some hints from some machine learning models. For example, how to construct a primal solution and so on. And also over time, as you collect more and more training data, these hints become better. So hopefully the performance of the solver also improves over time. So in this talk, I will present two works. The first one is kind of what started us in this project, which was we tried to come up with machine learning strategies for learning to solve the security constraint unit commitment problem. And then after we had some success there, we started to try to make these techniques more general, and we developed this open source framework, MIPLearn, which I'll talk after that. So let me just start from this initial research that we had on learning how to solve the security constraint unit commitment problem. So if you're not familiar with this problem, it's essentially one of the most fundamental problems in power systems optimization. It's used very widely to clear the electricity markets, but also in a lot of other applications. And the problem essentially asks us to come up with a production schedule for generation. So you have two sets of main variables. One set of variables decides which generators are on at each time of the day. And the second set of variables decides how much power does each generator produce at each time of the day. So we have these binary variables, and we also have some continuous variables. And then we have a lot of constraints. One of the constraints, for example, is that the production must satisfy the demand. The other constraint is that we have to compute power flows, and we have to ensure that all the power flows are within the safe limits, so we cannot exceed the transmission line capacity. A third one is related to the security part, which means that if you lose one transmission line unexpectedly, or if you lose a generator, the production still has to be somewhat feasible. And then you have a lot of other constraints, such as you cannot switch on and off a generator all the time and things like that. So it's a very large-scale problem. It's a very complex problem, a lot of constraints, but it's also very important. So we are trying to see, can we use machine learning to accelerate the solution? What we proposed were three different strategies aimed at three different aspects of the problem, which we think are hard and could benefit from ML. So the first one was about these transmission constraints that I just mentioned. So these transmission constraints are essentially a linearized version of the AC power flow. It's called DC power flow. And the thing about them is that they are typically extremely dense. So if you add too many of them to your problem, it really, really impacts the running time. And another bad thing about them is that there's a very large number of them. But the good thing is that most of them are redundant. So we could use a lazy constraint generation approach. But even if you do that, it still takes time for us to separate the constraints, to add them to the problem, and it might take a lot of iterations. So the first thing we try to study is, can machine learning find a set of non-redundant transmission constraints to add to the problem? And the strategy that we used here, which was successful, was using just k-nearest neighbors. So essentially, we solve a lot of similar instances. For each one of these instances, we see which transmission constraints were necessary. And then when you give me a new instance, I try to find in the data set which ones are the most similar, and I see which constraints were required for those. So if a constraint was required often enough, we enforce it ahead of time. If not, we don't enforce it. So I will show some benchmarks here, and I'm going to compare against a few baselines. So the first one is just the lazy constraint method, which is described in detail in this paper. But we also try a few others, such as what if we just add all the constraints for the most similar instance we have in our training data set? Or what if we enforce all the constraints we have ever seen in the training data set? And finally, for all the benchmark that I'll show in the future here, I also have this perfect method, which essentially cheats and knows what the answer is and enforces exactly the correct constraints. So the reason I add this is to know how far away we are from the theoretical optimum. So if we are very close already, then it makes no sense to invest a lot of time on more complicated machine learning models. But if there's a gap, then we might have some opportunities to improve.
Álinson, can I ask a question?
Oh yeah, go ahead.
So here, to retrieve a constraint using k-nearest neighbor on historical training instances, you assume, or by design, these constraints are kind of, it's the same constraint set, right? So there's no, you don't need to kind of generalize. Just like you look through the database, you see the some measure of similarity of instances, I guess, and then you say what worked there might work here.
Yeah, exactly. I'll touch a bit on this in the future slide, but essentially, we assume only some minor variations in the input data, such as different objective functions or different right-hand sides. But we assume roughly that the variables keep their same meaning.
Yes.
And we don't need the constraint itself to be like portable across instances. But we do need some representation of the constraint which is transferable. So we can regenerate the constraint. For example, maybe if the network changed a little bit, we know it was the constraint for this transmission line at this time step. So we can regenerate that.
Okay, great. Thank you.
So there's a little bit of generality, but not very much. Yeah, so here are just some benchmark results. I'm not going to show all the details. I can discuss this later if you want to. But essentially, we took some large-scale data sets. We also generated some realistic variations in the input data. And these are the results that we got for the transmission constraints. So what we saw here was actually that this is a pretty easy prediction task. It was a bit surprising to us, but pretty much all the methods performed well, even just collecting all the transmission constraints that we ever seen in the past. There are not a lot of them. So essentially the set is relatively stable over time, which is nice to see. But if we do use a slightly more advanced machine learning models, such as k-nearest neighbors, we can obtain better performance than just these very trivial strategies. And we also saw that the performance was almost exactly the same as the perfect. So there's a bit variation here, just some random noise. So essentially, k-nearest neighbors is performing almost exactly near perfect performance. And just with this little strategy, we can already get a 2.8x speed up on security constraint using. The second thing I'd like to focus on are now, of course, warm starts. So I think most of you are already aware of this, but the solvers allow you to provide an initial solution, which can be quite useful for the solver to prune the search tree and also to know when to stop, right? The drawback of warm starts is that it's pretty hard to construct them. Usually you need some problem-specific heuristics. You need to think a lot about it. So what we tried to do here was to try to construct some high-quality warm starts using machine learning. And it's also similar to the previous strategy that we had before. But the main difference here is that now we can also construct a partial warm start. So what we do is we see the most similar instances we had in the past. And then for each variable, we see whether essentially the machine learning can predict that variable well. If it can, then we set that variable as in the warm start. But if it turns out there not be a consensus, maybe a lot of instances were 0, a lot of other instances were 1, then we essentially leave that for the solver to decide. So there's one nice thing is that we don't have to predict the entire solution. We can predict just a partial warm start, and the solver completes it. So a few alternative strategies that I'm going to show here are the baseline, where we don't provide any warm starts. The collect K, which is essentially we just collect the entire warm starts, and we provide not just one warm start, but actually the solution to all the similar instance variations. We also compare against the perfect predictor, which just provides the optimal value for all the binary variables. And here are the results. So I'm applying this on top of the previous one that we had, where we predict the transmission constraints. But essentially, we see that if we just collect the previous solutions, it works a little bit to some extent. But if you try to collect large number of solutions, for example, if you provide 15 solutions to the solver, then just the time it takes to process those solutions, it already starts to add up, and then you don't get a lot of speedups. Whereas if you try to essentially combine the solutions into one partial solution, you get much better speedups. So here we improve the speedup that we had before all the way up to 4.3. Another interesting thing was that using this strategy, all the warm stars we generated were actually always valid and optimal after the solver completed them. But we didn't get the same speed up as the perfect method because it took some time for the solver to complete those warm starts. So essentially, this difference in time here is just the time it took the solver to complete it. But it was also a strategy that worked pretty well. So up to this point, we have around 4x speedups. For other instances, around 5. But now I'd like to talk about the third strategy that we have, which is a bit more aggressive, which is can we actually, if we don't require optimality guarantee, can we actually restrict the search space and help the solver find a solution even faster? Because what we observe in the SCUC solutions is that they have a number of patterns. For example, some units are always on, some units are always off. And also we notice that state transitions don't happen very frequently. So this third machine learning task would be, can we find some of these hyperplanes where the solution is very likely to be? And can we actually enforce them? So for this, we also train one machine learning model for each constraint that tries to predict, like, given this input data, is this constraint likely to be satisfied? And one extra thing that we do here is in the training data self itself, we evaluate how good those machine learning models are. If it turns out that the machine learning model is not very good, we discard it, we don't trust it at all. And we just keep the ones that provide us, that has a very good accuracy. So in the following slide, I'm going to show you some results. And I'm going to compare against the baseline where we don't enforce any of these equalities, and another one where we actually fix all the binary variables to the optimal values. And you can see here that if we do that, if we enforce those equalities that the machine learning is able to find, then we are able to improve the speed up from around 4 or 5 to about 10x. And another thing that we notice here is, although we did lose optimality guarantee, we didn't see any degradation in the actual solution quality. So our Meep gap tolerance was 0.1%, so everything was within that gap tolerance. And yeah, we got some very good speed ups. On the other hand, we do see that there's a long way to go for the perfect. Of course, if you're able to fix all the binary variables, then you get even higher speed up. And one last comment that I have here is that if you don't do that kind of cross-validation and you just blindly trust the machine learning models, then the results were really quite terrible. Essentially, 76% of all the instance variations became infeasible because you're now enforcing things. Yeah. So these were the results that we got for our security constraint unit commitment. And now I'm going to move on to the MIPLearn. Does anybody have any questions in the chat? I can answer before I move on.
I think there was a question in the chat. So the question was, how do you measure whether you can predict the value of a variable well? I think it's about the consensus idea, maybe.
Oh, the consensus one? Yeah, so essentially this is a very simple strategy. So we just see the most similar instances, and we see what was the value for that variable in those instances. What was the optimal value? If they reach a certain amount of consensus, for example, 95% consensus, then we trust that that is very likely to assume that value. If there's no consensus, then we don't set that value. But for fixing for these hyperplanes, we actually apply k-fold cross-validation, and we see what is the accuracy and the recall of the precision, the recall of these machine learning models. If they don't significantly outperform a dummy predictor, then we discard those constraints. We don't try to enforce those constraints.
Maybe as a follow-up, this cross-validation, you mentioned in the next slide that if you remove it, then this doesn't work. But yeah, the cross-validation, is this done on a per instance? I didn't understand the level at which the cross-validation is applied.
So I guess in the first step, just with the training data set, we tried to train these machine learning models on a subset of the training data set, and we evaluate on the remaining portion of the training data set. If it performs very well on that remaining portion, then we know that constraint is likely to be easily predictable. So we then decide to use that.
You do it, so the cross-validation is on a per constraint
It's
basis?
all the training data set, yeah.
Okay.
Yeah. And then if we assume, for example, xgt equals 0 for a certain generator at a certain time, we can actually predict that very well. Then we train on the entire training data set and we apply it during the test.
I see. Okay.
Yeah.
And there's
so it's
one
just to rule out the constraints that are very volatile, that we cannot really predict that well. So we don't even try to.
Okay. And maybe one last question before you move on from Harsha. What was the size of the system you were testing on for SCUC?
Yeah, that's a good question. We tested on instances from 1,800 buses all the way up to 6,500 buses. We also had the full N-1 security constraints. So these are pretty large instances. Yeah.
Okay.
We also have the paper out already on IGRC, so if you want to know all the details, we have them there. But I can also discuss afterwards.
All right, great.
Yeah. So after we finished this work on SCUC, we would think that a lot of these techniques that we implemented are not really specific to unit commitment. They can really be applied to problems in general. So we started to develop an open source framework to, our goal was twofold. The first one is to make those techniques that we implemented for UC to be more widely applicable. So if you have any other problem that you think you could benefit from these things, you can just use it. You don't have to spend a lot of time re-implementing. And the second and more ambitious goal of this MIPLearn framework is also to kind of provide a platform for future learning enhanced optimization work. So if you are a researcher in this area and you're trying to implement some new methods or some new models, you don't have to start from scratch. We try to make this very extensible so you can actually provide your own ideas to it and you extend it. So I'll go over it. So the MIPLearn framework is, as I said, is a framework for essentially combining Meep solvers with machine learning models. Some of the main features are that it's actually a multi-language framework. It's programmed both in Python and in Julia. It also supports multiple modeling languages. So we currently support Pyomo, gurobipy, and Jump. So if you're currently solving any optimization problem using these modeling languages, you can integrate it with MIPLearn. And because we go through these modeling languages, we have broad solver compatibility. So we currently support all the major commercial solvers, including Gurobi, CPLEX, and Express, but also a number of open source solvers such as SCIP, HICE, CBC. So essentially, if the modeling language has access to those, we can also use your solver. Another thing is that this is not problem specific like unit commitment. You can actually define your own problems. You can bring your own formulation. And not only that, but the machine learning models themselves, you can also specify. You can just use some basic ones from scikit-learn, or if you have some more advanced ones that you implement yourself, you can also use that. Another thing is we saw it was pretty hard to evaluate the performance of these methods using the existing instances. So we also have a pretty large library of random problem generators that you can use. I'll mention this later. And a few strategies that we already have implemented are related to primal solutions, like I mentioned before, like predicting warm starts. We also have lazy constraints and cutting planes. And we also have some experimental work on branching bound and branching strategies. So the package is already available today on GitHub. And if you go there, you also see pretty extensive documentation. We have actually a full tutorial for each one of these modeling languages, Pyomo, gurobipy, and Jump. You can just follow along and see how to use it. So let me just briefly go over all the main components. So the first thing that I mentioned are the benchmark problems. So when we started to study this, we saw that there was actually a limited number of available Meep instances. I mean, there are some very good benchmarks out there, like the MIPLib 2017. But these learning enhanced optimization methods, they usually benefit from even more instances than that, like maybe tens of thousands or hundreds of thousands of instances. So it was good to have problem generators. Another thing is that it was somewhat hard to find homogeneous set of instances. If you filter, for example, MIPLib to just one particular problem class or even a particular size range, then it becomes very small. So what we provide here are problem generators for 9 different problem classes in different categories. And we allow you to actually specify how should these instances be generated. These are not hard-coded. You can, so here I have a small example for the p-median problem. You can specify where to generate and how should the cost be and everything. And another thing that makes this quite different is that you configure how homogeneous you would like your data set to be. If you just like to be one instance with minor variations to the objective function, you can do that. Or if you just want, for example, give me 10,000 TSP problem instances of different sizes, of different graphs, you can also do that. So they are highly configurable. And for each one of these, we also provide the gurobipy formulation. The second thing that I would like to talk about is the training data. So now that we have the instances, how do we collect the data that we're going to use to train our machine learning models? And a few challenges that we had here is actually related to software engineering challenges. Collecting this training data is usually involves handling large number of large files. The data you collect is also very heterogeneous. Sometimes the matrices, lists, so it's hard to keep things organized. And it's also very expensive to regenerate. So the way we do it in MIPLearn is we split it into 2 phases. First, we have the collection phase, where we solve the problem and collect all the data that we think is going to be useful in the future. So specifically, first we load the problem, and then we collect all the static information about the problem. Then we solve the LP relaxation, we collect all the optimal LP information, and then we finally solve the Meep, and we collect the optimal Meep information. And then there's all stored in HDF5 files. So this is the first phase, this is the collection phase. And then in the training phase, you now have all this raw data collected into these HDF5 files, and now you actually extract. And what I mean by that is you pick out of all this data that I collected, what exactly am I going to use, and do I need to do any conversions, or do I need to do any further computations? So these are what we call extractors, and these essentially produce the matrices that you will feed to your machine learning models. So these extractors can extract features at a variable level, at a constraint level, or at instance level. And we also have implemented a few in the literature, such as this paper here from 2017. But we are open to implementing new extractors too. And the way the reason we split into 2 phases is that if in the future you decide to add a new feature to your machine learning model, you don't have to repeat the collection phase, which is the most expensive. Okay, so this is the training data collection. Now I'd like to talk about one of the main components that we have, which is predicting primal solutions. So just like we did for unit commitment, I mean, warm starts are useful for a number of problems. So we have implementation of a few different strategies here. Let me just go quickly over them. So the first one is called a memorizing primal component. So what this machine learning component does is, after you have solved all these training instances, it memorizes all the optimal solutions that you have seen in the past. And then what it asks the machine learning is to give you a score on how good the solution is likely to be for your current instance. Okay, so you don't try to construct new instances. Sorry, you don't try to construct new solutions necessarily. You just look from the previous ones that you had, and you try to match them to your current instance. We also have the independent variable primal component strategy, which essentially trains one machine learning model per decision variable. And so each model tries to predict the value of each independent variable. We also have one which is the joint vars. Essentially, you only have one machine learning model that tries to predict jointly the values for all the decision variables. And finally, we also have the expert. For all of these components, they are highly configurable, so you can actually provide your own machine learning models. This is just a meta strategy, right? You can then specify, oh, I want to use a neural net, or I want to use just logistic regression, for example. You specify that. And you also specify what do you do with it after you compute the solution. You can do a few things, such as set warm starts. You can fix the variables to the values that you predicted. We also have this action called enforced proximity, which is essentially says the solution has to be not very different from the one that the machine learning model predicted. So essentially, it can differ in at most a certain number of binary variables. Okay. So this is one of the main components that we have. But before I show another one, I'd just like to show you now that we have all of these, how do we put everything together? So if you actually want to solve the problem using MIPLearn, these are roughly the steps that you would do. So the first thing you do is to define your problem. So you have a function that accepts a data structure and constructs the problem, such as adding the variables, adding the objective function, adding constraints. And then in step 2, we are using a problem generator here, so we generate a lot of instances. You can also use your historical data if you have that. But here we are generating some random instances, we're saving them to files. And then in the third step, we run the collector. So essentially, we solve each one of these. We generate those HDF5 files with the training data. And because this phase is usually very computationally expensive, we actually allow some parallel processing. So you can also say, just run 16 of these in parallel, and MIPLearn will do this for you. And then in step 4, you actually define what strategies would you like to use to solve new instances. So the way you do this is you create a new instance of this learning solver object, and you provide what components would you like to add, such as the memorizing parameter component that I mentioned before with all the configuration parameters. And then you fit it using the training data files. And then finally, at step 5, the final step is you can use the same solver that you just created and you fit to optimize a new instance. So you just provide a new data file and the function to build your model. And if you run this, you will see something similar to this, which is just a Gurobi log file. But you can see here that in the middle, Gurobi seems to be using a warm start, and this warm start was computed by MIPLearn. So essentially, it looks very similar to just using the gurobipy interface. The difference is that you have these fit calls here in the middle, and then you can optimize it later. So now let me just talk about a few other more advanced components that we have. So the other one I'd like to talk about is related to lazy constraints and user cuts. So just like we did it for unit commitment, we also have it implemented here, which essentially is the machine learning task is if I use lazy constraints or if I use user cuts in my problem, can I predict which ones are required ahead of time? And for this, we provide 2 strategies, the memorizing strategy and the expert. So the memorizing is the same one that we use for unit commitment. Essentially, we solve the training instances, we see all the constraints we ever used in the past, and then we ask the machine learning model to assign a score, or essentially to decide which one of these are likely to be very useful for my current instance. Okay, and then the expert is just it just cheats and looks at the ones that are actually necessary. So if you actually want to implement this in the model, it's very similar to how you would typically implement a lazy constraint approach. So you just have your original problem definition here. And the only thing you need to change to use it with MIPLearn is you need to split your callback into 2. So usually in a callback, you would first separate the constraint or the cuts, and then you would immediately enforce them. We just ask you to do these into 2 separate methods. So the first one is you just separate, and then you return the constraint identifiers. This can be anything that you will use later to actually create the constraint. And then in the second method, we provide you the list of constraint identifiers, and then you enforce them. And the reason why we split it into 2 phases is because when we're actually solving the problem, the first time we get into the callback, we will not call your callback. We will actually run the machine learning model. The machine learning model will predict which constraints should be generated, and it will just immediately ask you to enforce a lot of the constraints without even running the separation procedure. And then later, if further separation is required, we will use your original callback. Okay, so there's just one small example here. And just like the components that I mentioned before, this is also highly configurable. In particular, you can provide your own machine learning model to decide which constraints. And I do want to also mention this again, but how you represent the constraints is really up to you. You can, for example, just provide the list of coefficients if these coefficients are portable among instances. But if you have some more advanced representation, for example, maybe just generate all the constraints for generator 1. You could also just do it something like that. Okay, so the constraint representation is actually user specified. And these are the main components that we have. We are also now doing some further research, and we are experimenting with a few other things. So I'd just like to mention these. If you go to our documentation, you're not going to find these yet. These are still work in progress. So one thing that we are currently working on is also learning enhanced branching. And one challenge we saw there when we studied that was really integrating things with the solver. We initially tried to do this using CPLEX. We spent a lot of time on it. I know also a lot of people try to integrate it with SCIP, and it can be done. But if you're really just trying to quickly prototype new methods, that can be quite time consuming. So what we provide in the Julia version of MIPLearn is a simple implementation of a branch amount method. It's completely solver independent. It has multiple branching strategies. And we're using this mostly just as a prototype. So if you don't want to read thousands of lines of code in SCIP, if you just want to quickly prototype something, we have this. And also, if you just want to collect training data and then use this training data to provide to a state-of-the-art solver, you can use this. What we're using here, current work that we're doing is trying to learn to branch on general disjunctions. Another work in progress that we have is learning his Tableau cuts. So if you ever try to implement that, you know it can be pretty hard to implement. It can also be pretty hard to integrate with a solver. So we also provide some functionality based on that. We have some implementation of Tableau cut generation in Julia. It's completely solver independent. And one nice thing about our implementation is that if you give me a problem in any form, we can not only convert it to the standard equality form and generate the cuts, but we can actually bring those cuts back into the original variable space. So you can then provide it to a state-of-the-art solver. So essentially, this can just be used in the initial phase when the machine learning model predicts what cuts to generate. We can then generate the cuts and provide it back to a state-of-the-art solver, right? And the work that we're currently doing with Georgia Tech is how to generate GMI cuts from multiple bases. So this is just a very brief overview of the framework we are developing. It's completely open source. It's already available on MIPLearn. I would just also like to mention here that this is really open source. And if you have any comments, any questions, or even pull requests, sorry, mistyped it here, they are really very welcome. And if you, for example, see something that we're missing and you think you would like to contribute to that, that's really, really welcome. So some future work that we're currently working on, as I mentioned, some additional machine learning acceleration strategies. We are also planning to extend this package to nonlinear optimization because a lot of these methods would also work there. And a third thing that we're working on is actually, it can be hard for the users to decide how to use machine learning. There are so many options. So one thing that we're doing now is actually integrating with some problem-specific optimization packages. And we have already started integrating with one package that we developed called unicommitment.gl. So essentially, because we know the problem, we can know ahead of time what strategies work the best and how should the training data be collected and all that. So we think there's also another way that this package can be used. So if you have a problem-specific package that you would like to incorporate machine learning into it, you can also use MIPLearn. And finally, I'd just like to acknowledge that this is being sponsored by the DOE Office of Electricity. And with that, thank you very much for listening. I'll be happy to answer any questions.
Great. Thank you very much.
Thank you, Álinson. We do have a couple of questions in the chat before we go into the breakout rooms. Harsh asked, in the problem generator step.
By the way, if Harsha wants to unmute and maybe ask.
Oh, yes. Let me see. Everybody has the option to unmute. So, yes, you can ask Harsha.
Sure.
Like to ask yourself.
Thank you. Hi, Álinson. Very nice talk. This is Harsha from Lanel. I had a quick question in the slide 16, I think, on the problem generator step. So in this, so there is this input MIP model, right? So which kind of you build a model with all the necessary variables and constraints and objective function, and then there is the second step where we basically where the package like around it generates around 100 instances, right? Which so are these the instances which are like from some sort of an inbuilt library of MIP instances which are somewhat similar to this instance, or are these kind of the randomized version of the input MIP model, what is in your the build model step?
Yeah, so this little example here that I had is what if you want to use one of the problem generators that we provide. So let me just go back here. For example, this is what the p-median generator looks like. So you can specify all the parameters and it will generate some random instances for you. So if you want to use one of the provided problem generators, you can. If you have your own problem generators, you can also do the same thing. You can have a look at how did we implement ours, and you can implement your own. But if you also have just historical data, you can also just directly, instead of generating, you can read them from the files, right? So there's just one way of doing it. There's just, if you want to use our generators, this is what it looks like.
I see. Wonderful, wonderful. So, but I remember, I think you mentioned as a follow-up question to this was, step 2 is going to be a little bit expensive, right? Because this is where you're actually training it.
Yeah, step 3.
Step 3, right. So once we do this training, so let's say I would like to run like few other MIP models, right? After not just this one MIP model. So is this something which you could actually save as an information and then reuse that for newer instances when we run, so that you actually don't have to retrain?
I'm not entirely sure I understand the question, but if you just, yeah, so at this point here, after you train, you have all these HDF5 files, right?
Correct.
So in the future, if you rerun this script, this basic collector is clever enough to know that these files were already processed. So we'll just skip the ones that are already processed.
Oh,
so this will actually be very fast. But if you want to do this in an incremental way, so maybe you already have 100, and today you solve 10, and you would like to add those, you can essentially just do the same thing again. This will solve the new additional files, and it will fit using all of them, including the old ones.
Oh, wonderful. Okay. Thank you so much.
Yeah, thanks for the question.
And maybe one more before we jump in and the recording. Ibrahim, do you want to unmute, or do you want me to ask the question?
Thank you. So you mentioned that there is a branch unbound independent from any solvers implemented in Julia, right?
Yeah.
So could it be accessed like through the Python version, like with an API or something, or should it be re-implemented in Python too?
No, so this is only available in the Julia version of the package. And the main reason is that the performance there was very important for us, and also the parallelization. So it was pretty hard to do it in Python. So that's why we only have it in the Julia version of the package. But I think I also saw some question related to, if you use this, can you use it with a state-of-the-art solver? And the main idea here is, if you're just a researcher trying to experiment with some learning enhanced branching rules, then you would be able to experiment with this, which is much shorter code, much easier to modify. Yeah.
Yes, because as I have many solvers do not allow
yeah, exactly,
branching callbacks for inside the model, like branching.
Yeah, so I do have a follow-up on that. One thing that we are doing here is actually, we just use this during the training phase. So just to give you one example, we did some early experimentation with branching priorities. And a lot of solvers accept branching priorities, right? But it's hard for us to compute effective branching priorities if we don't actually control the branching bound method. So essentially, we can run the training with our simple branching bound just to figure out the branching priorities. And then we provide the branching priorities to the solver, to the state-of-the-art solver. So that's one possibility. And also the work that we're doing now on branching on general disjunctions is somewhat similar. We just use this simple solver to collect training data to learn the disjunctions, but then later we can generate some information that might be useful to provide back to the state-of-the-art solver. So yeah, unfortunately, we cannot control the branching in the commercial solvers today, but at least I think we could generate some data that might be useful for them.
Thank you.
Yeah, thank you.
Okay, well, let's stop the recording here, but please stick around for our Zoom social session / more questions for Álinson session.
Yeah.
And I also want to remind you that there is going to be one more session of dots coming up in a month. So the first Friday of December. Stay tuned for the announcement over our mailing list. Some of the emails may be going to your spam, so tell your friends to check their spam folders, whitelist us, and so on. So, but yes, thank you everybody for joining, and stick around.